Good morning, students. Well, it's almost to that time of the year where you get a subtle break, and for some of you it may be a longer break. It just really depends what your plans are for the summer. But one nice thing about the college curriculum is that the semesters are finite, and we we move from the beginning of the semester to the end of the semester thinking, the end will never come, and then boom, here it is. So um, remember, the final exam testing window is the same as it has been for the entire semester. No confusion. I was thinking about doing it earlier. That would certainly be maybe more beneficial for some students, less for others. But I just decided that if you have the maximum amount of time to prepare, that gives you more flexibility, because I'm sure with your other classes, the flexibility that I have provided through the semester is certainly not the same. I know this, I can say that with confidence. I demand a lot of you, and so I give you time to study. With that said, the final exam will contain 20 questions. The final exam is comprehensive, okay? It is an impossibility to put every type of example on the exam that we have covered in the class, clearly. So the exam will cover the large topics of the course, the basic fundamentals, things that I have stressed, things that are important in pre-calculus. So if you've done your work during the term, there should be no issue whatsoever. Just remember that in doing a math class and preparing for a final, you have elevated your ability to critically think in pre-calculus. So don't just assume that, oh, well, I'll only do the problems I've seen before. No, you read the problem, you react to it, and you execute the problem. That's what a STEM professional does. That's what a math major does. And for the, when you look at what you have to do in the STEM career and the STEM curriculum, most of you have to end up being a minor in math just to get through all of the courses that are required of you. So just keep that in mind. Now, I did give an extra day for the last two homework assignments. At this point, there will be no more extensions. I appreciate your willingness to ask for extensions. Sometimes it gets out of hand, and I just want to say at this point, don't ask for any more. I've been very generous throughout the term. You need to complete your homework as it's scheduled. Uh, Again, the one very important thing about a college class, and you have your more difficult classes, your easier classes, the classes that are in between, it varies for every student. So someone can say, oh, that's a really hard class. And you might say, oh no, that's fine for me. But the bottom line is that we stay current, that you stay current and you follow the schedule. When you become a university student, some of you will complete your university degree and then possibly go on to do graduate work. Following a schedule is essential. When you get your STEM professional job, that will also be very important. It's not a matter of always saying, okay, well, this happened, it's understandable. But in the grand scheme of things, we have to meet our obligations. And so I've tried to be very generous throughout the term. I haven't tried, I've been very generous. But at this point, there is there is a cutoff, and grades must be halted, and then we move into the assimilation process of grades. Remember, the formula for the grades is clearly stated on the syllabus. The grades are computed as I have dictated throughout the entire term, and where your grade lands, that's the grade you get. I do not round. I have never rounded. It is completely and academically unethical to round. Your grade is what it computes to be, okay? I've had this discussion with many students, and the interesting thing is that most students think they know more than the math professor, which again is absurd. Ladies and gentlemen, when you complete your education and you have your advanced degree, then you can be in a position where you can be the authority. But until that point, it is important to respect the expertise of your professors. And even for you individuals that are in the early college, high school, to respect your high school professors. I know that in general, respect for professors and teachers is very low, and that needs to change. So just remember, when it's all said and done, go back to the high school, go back to the college, and thank all those really dedicated professionals that helped you get to that finish line. I remember in high school, I went back to do some substitute teaching and I went around to all of my teachers and said, thank you. And they thought, well, that's interesting. I just said, I want to say thank you for putting up with me. And they said, oh, but Ron, you were a good student. I said, but you know what? You always stood behind me and you always offered support and you challenged me. And that really had a big impact on me, ladies and gentlemen. That is exactly why I teach the way I do. And I do hold you to a very high standard. We are obligated to have civil discourse and work to meet the standards of the class. And San Jacinto College is a very worthy place to do work. Again, we are a top 10 junior college. We do have high standards, but a degree here will carry weight. So I appreciate all of your hard work throughout the term. I appreciate your industry. I appreciate the fact that you want to make a difference, okay? Now, when you study for the final, do not go over material that you already know. That's not a good use of your time. Focus on the new material if it's still not mastered. Focus on aspects that have become rusty. For instance, if you just always need to go back and review trig equations, or it's like, you know, those logarithms, I need to review logarithms, or that new stuff with the binomial coefficients, you know, I need to review that. Focus on the concepts where you need review. Don't just kind of, you know, listen to your music and look over the test and say, oh, I know how to do that. That's not going to help. If you're going to do that, you might as well just take a nap and chill out. So focus, you know yourself the best. Focus on the concepts where you know you need some review. And what I wanted to do today is just basically go over some highlights from the review test that's on Blackboard. And also on Thursday, we won't have a formal lecture, so you can sleep late. You can get up and do some review or whatever you want to do. But I will have said all I can say, and I will be sending out good vibes for you to do well on your test. So let's go ahead and look at some examples. I keep talking about the IPEVO, that it turned out to be really a good thing. And I like it because, like I said before, when things get upgraded, at first we're like, oh no, don't change it. It already works really well. But we all understand that change does help us to do things better. And I'm appreciative of IPEVO. Okay, now one of the things or the overriding themes in the class is just critical thinking. And so if you look at some of the review exercises on the practice final, some of them are quite straightforward and very simple. So what I wanted to do is kind of work backwards and look at some issues and examples that cover some of the newer material and then go back to some of the older material. So I get lots of questions about sequences and the proper form. So when you think about the final, there'll be like a highlight of the arithmetic, the geometric, and just the basic construct. So here's a very simple example, but it actually is very important. So we have I equals 1 to 5 of 3 times 3 to the I. Now, you know, when it comes to doing a particular example, a sum or whatever, you know, you can always just look at it and say, well, I can just write this out and add it up, you know, and that's fine. But if you're doing an example that requires a partial sum that's non-trivial, for instance, what's important here is that what we want to do is observe the fact that we have a geometric nth term here. This is a partial sum for a geometric sequence. Now, when we actually derived all these formulas, remember we worked pretty hard to do this. We always called A the first term. I'll use the same letters here. I think I used a K. So when we looked at the partial sum, we had something like this: the sum of the first n terms. And so we would have an n up here, and we had r to the n, well, actually, creature of habit here, let me use the letter that I said I would, I minus 1. And so this was the construct that we created. This was the convention. And then this turned out to be a telescoping sum. Most of the terms absorb, and we ended up with A times 1 minus r to the n divided by 1 minus r. And that was the partial sum. That is if we had this form here. Now, this is what's important. If you want to use this, then it must be reflected in this form, okay? Otherwise, this doesn't give you the correct answer. So now when we look here, we're thinking, well, we want to go ahead and use this form. So we're going to rewrite the exponents here so that it reflects this. We're seeing that the A and the R are quite related. So we're going to borrow. So just take one of the 3's away from the 3 to the I. So we're going to have 3 times 3. And then we'll have 3 to the I minus 1. Now, again, you can just write it out and notice that it's geometric. But again, the purpose of this is that we use the conventions that we constructed to make our lives easier. And so now we can multiply 3 times 3. So we have 9 times 3 to the I minus 1. And now notice here, all we've done is algebraically manipulate the nth term. We haven't added to the index or subtracted, or we don't have to balance it. That's changing the indices and all is very important when we need to do it. You know how to do that. But all I did here was just readjust this algebraically. And now when we look over here, we clearly have an A and we have an R. So at this point, we can say A equals 9 and R equals 3. And of course, N equals 5. So that gives you a blueprint. So again, we love the infinite case because with the infinite case, we don't have to worry about N. The partial sums are more complicated than the infinite sums. And so now we can just fill everything in, and we have 9. We have 1 minus 3 to the 5th power. And then we have 1 minus 3. So now let's go ahead and reduce this. Notice downstairs we have a 9 divided by a negative 2. And then we have 1 minus 3 to the 5th. Now we know 3 to the 4th is 81. So 3 to the 5th, we could just multiply 81 by 3. And that'll give us a 243. So this gives us a 2, 4, 3. And now, of course, the negatives, we can just absorb the negatives. We have a negative here and a negative here. So this will be 9 halves, 243 minus 1. So we have 9 halves, 2, 4, 2. Well, we love even numbers because, well, they're easy. So we have 9. So this will give us a 1, 2, 1. And then we can easily multiply. So we get a 9, an 18, and a 1. So when you look at this particular situation here, and I'll say this, when it comes to computing geometric and arithmetic partial sums, it's like working with the conic sections, and you all really did well with the conic sections. I mean, I was impressed. One student mentioned during a conference hour, oh, I get these conic sections. I said, well, good, you understand translation of axes. The one thing that's interesting, and if you have time, look into the translation of axes. That's a really, really nifty uh, exercise. It's something that when I have additional time, I will interject it into the curriculum in the regular class. I teach it in the honors section, but the idea is that I think you'll be fascinated by it because you get the juxtaposition of the conic section with the trigonometry. And math is just that way. There, you can study it infinitely, no pun intended, and never get bored. So when you look at this, you have a situation that really depends on the construction here. Now you can be very, very flexible with partial sums and the famous formulas, you know, I like the famous formulas, those help you to compute partial sums. So the idea is that, you know, you can sit here and write everything out and add it up, but as you work into the calculus and as you work into more engineering, we need to recognize this very, very important sequence. And so this gives you a routine to do this, albeit not very difficult, but you would be surprised. For instance, here's another important thing that I've noticed during my conference hours. Notice the index here begins at 1. If we alter that, that's fine. But if we alter that, then that changes what we have here. Okay. So again, you just have to be very careful that whatever you apply in terms of a formula meets the standard of the convention. Now, one thing that we found to be very useful is the following. That is in the infinite case. So say we had something like this, and I'll go ahead and just remind you, recall, if it turns out that we allow n to pass to infinity and the absolute value of r is less than 1, then this actually converges. So with this restriction, we can look at the infinite case, and this is something you're going to use in calculus too, maybe more than you would like. And so now what usually happens is that we can now use the n as the index because now it's just moved off to infinity. So we can say n equals 1 to infinity of a r n minus 1. So if you wrote this out, of course, this is just like the arithmetic. It looks like this. This is where it all began, right? AR squared, etc., ad infinitum. And then, of course, if you like, you can just stick in the nth term, but this goes on infinitely. Okay, so with this construction, then we just get A divided by 1 minus R. And this makes a good test question. For instance, when you had the ball that was bouncing, we did a partial sum. Well, maybe we could do an example where you just let it bounce forever until it stops. And that would be the infinite case, which again is infinitely simpler because you don't have to deal with the n. The n makes the problem a lot more complicated, at least algebraically. So for instance, if we had something like this on an example, maybe we have the following. We'll say, consider this sequence. So we have 2, and then we have negative. I'll just list some. I'll list this as items or particular elements of a sequence as opposed to the summation notation, something like this. And I just used the 3 idea that we had from this last one. Now, if we consider this, the question might say, compute the sum. So when you look at this, again, you see it's infinite, and you're thinking, well, this had better be geometric because it's really the only convergent infinite series that we've talked about in this class. I mean, the arithmetic will never converge. It's impossible for it to converge. And the famous formulas, well, some are arithmetic, they don't converge because what you're adding is not getting closer to 0 quickly enough. And what you're adding in those cases is just getting bigger and bigger each time. So that's like saying, is this series going to converge if I keep adding larger and larger numbers? No, clearly not. So when you look at this, you're thinking, okay, well, this is geometric. And how is that? We see the first term is 2. And then this is set up, we can just look at a ratio of 2 terms. You don't even have to guess. So we'll just say, in this case, -2/3 divided by 2. Look at the ratio of A2 to A1. And notice the 2's absorb, and we clearly get a 1/3 with a negative. So now, of course, when you multiply by -1/3, you get -2/3, another -1/3, 2/9, the negatives absorb, then -2/27, and then, of course, 2/81. It's going to alternate. This is basically an alternating series. So now you're thinking, oh, okay, well, we could do this now. So if you wanted, just as a little extra practice, you could say, all right, well, let me fit it like this. We'll have n equals 1 to infinity, and we'll have the 2, and we'll just have the -1/3 n minus 1. So this would be writing this with this convention that we have here. Again, it doesn't matter that you don't write it this way. It just opens the door to this formula. And later on, you'll see many series that will begin at 0 just for convenience. Okay, so the idea, just to make an adjustment here. Say you were looking at this and you said, I would really rather that this would just be n. So you're going to replace n with n plus 1. Okay, so if you do that, so basically n is replaced with n plus 1. And if we do that, then of course the n minus 1 just becomes n minus n plus 1, which just gives you n. So again, let me just say here, upon substituting, we have n plus 1 minus 1, which equals n. So that's going to give us the power we need. So this is an increase. We say an increase by 1. And so then the index would need to decrease by 1 to compensate. So this would give us the sum n equals 0 to infinity to -1/3 to the n. Okay. Now, here's the thing. As long as we start with this, we're okay, but we have to know that this is equivalent to this. And since this is equivalent to this, we know this is the sum here. So when we go from here to here, for instance, when n is equal 1, we have -1/3 to the 0. That's 1, we get a 2. Here where n is equal to 0, we get 2, -1/3 to the 0, 2. We get the same thing. These sums are equivalent. They have just been re-indexed. But since we know the sum of this is just an equivalent series to this. It has the same sum. So in order to use a formula, we need to convince ourselves that the actual form is maintained. And so that's what I'm trying to focus on here. When you get to calculus 1, you've got to be careful about if you use your famous formulas that they begin at 1. When you get to calculus 2, you have to be careful about what it is these sums actually represent. And it's not overly difficult. It's just a little bit of busy work. And that's all it is. I mean, we are comforted by the fact that most of what we do with sums is just like what we do with equation solving. You know, the same types of rules apply. And so now when we look at this, we can get the sum. So let me just write it down. So this implies, I'll just take this and rewrite it here. N equals 1 to infinity, to negative 1/3, n minus 1. So now we just fill everything in. We had the a and the 1/3. So we have this formula here. So we've got 2, and we have 1 minus a negative 1/3. So this gives us 2. So this will give us a 4/3. So we have 2 times 3/4. Again, the 2 absorbs into the 4, and that gives us 3/2. So the infinite case in calculus is very interesting. So what you're seeing here is that you can't always intuitively decide what the sum's going to be, because what we're seeing here is that we have the addition of some negative terms, but these terms are clearly getting closer and closer to 0, and they're getting there quickly enough so this actually converges. And so, as opposed to diverging to infinity or negative infinity, or it might be the case that we get a series that just jumps between two numbers. I mean, the idea is that if we say a series converges or a sequence converges, then the terms converge to that number. They get closer and closer and closer to that unique number, that unique limit. And so here, again, very simple, but as I've done my work, I've always adhered to the fact that we have these conventions. That's really the precision of STEM mathematics. If you do not follow the conventions, then your work is inconsistent. And that's what I've tried to teach throughout the term. And so again, hopefully this kind of gives a little better light to that. Now, one thing that I find to be fairly interesting, again, with the partial sums, will be the famous formulas. And so this will be example that you'll probably see on the test. So when it comes to summing, if I make a notion that says, okay, compute this, I mean, for instance, if you're doing your work and you write out all of the terms and you do add term by term and you show me that might be a long-winded way to do it. But if I actually specify that I want you to use the theory of a particular sequence, I need to see that. So for instance, here's an example that's useful. So we have something like this. Again, this is going to be a partial sum. We'll say n equals 1, let's say to 15. And we have 2 n squared minus 3. Now, and this problem would say compute the sum. And I could say use famous induction formulas. Now, again, if I say use the famous induction formulas, you have the sum of the first n natural numbers, the squares, and the cubes. I gave you those formulas. So one formula that turned out to be very useful looks like this. I equals 1 to n. And you can prove this by induction, even though these are fairly simple. We have I squared. So if we sum the first n squares of the natural numbers, 1 squared plus 2 squared plus 3 squared, we had this interesting formula, n times n plus 1 times 2n plus 1 divided by 6. So this would be a p of n. This is a logical statement about natural numbers, which can be proven either algebraically or by induction. And like I said before, students, there's a thought that says, well, if you get a nice algebraic proof, you just have to finish it off with induction. that is probably true in the most pure sense of doing mathematics. But most of us are happy to be grateful that we have an algebraic manifestation of a formula, and we go with it and say enough is enough. But if I say use the famous induction formulas, this would be good. Of course, if this number gets larger and larger, these become really, really important. So this again is what I taught you about the algebra of the partial sum. So when we look at the algebra of the partial sum, we can just break it down into two pieces and factor the constants. So the first step would say, okay, we have n equals 1 to 15, 2n squared. And then we have plus, I'll just do this in all the steps. And we just have what? -3. Now, when you look at this, you're thinking, well, you're adding -3 to itself 15 times, or you can just go ahead and factor the constants. So we'll have 2 n equals 1 to 15 n squared. So this would be famous formula. And notice again, index beginning with 1. So this fits this. This is equivalent here. Again, I'm using different letters, but it's equivalent. And that's important. And then, of course, we could have what? Plus a -3, and just write the last sum as adding 1 to itself 15 times. So that's equivalent. Again, when you break up the partial sum, just remember, ladies and gentlemen, finite sums always converge, right? Finite sums always converge. If you're adding a finite number of real numbers, it necessarily converges. And you might say, well, I've got 2 trillion terms in my sum. Okay, well, it converges. The thing is that infinity is smaller than no number. Infinity is a behavior. You throw out the largest number that you can think of, infinity will surpass that. So when we're working with infinity, that all of these brilliant minds decided that infinity is actually something we need to understand. That's where the arithmetic was born of the calculus. The Greeks understood this in their geometric ways, but we don't always think about the power that we have with the mathematics. So now when we look at this, we're like, okay, well, we can use the famous formula, the induction formula, and we've got a simple formula for this to complete the problem. So now we have 2. Now we've got this formula. So we'll say n times n plus 1, 2n plus 1 divided by 6. And then you can do a little vertical line and just say n equals 15. This is kind of an old notation. It just basically says, don't write down the formula and substitute at the same time. Write this down so you have something to check and know that you replace n with 15. And then, of course, this one's easy. We just have -3. We add 1 to itself 15 times. That's just 15. So that part's simple. So now notice the 2 absorbs into the 6. That gives us a 1/3. And now we can fill in the 15 here. So we have a 15, we have a 16, and then of course 2 times 15 is 30, plus 1 is a 31. So that is probably best to write this and then write this, minus a 45. So now, of course, the 3 absorbs into the 5. So we have a 5 times a 16. And then we have a 30 plus a 1 minus a 45. So now here, of course, that'll be a 3. That's an 80, right? 15 times, or 5 times 6, 16 is 80. And so we have 30 plus 1 minus 45. So here we get a 24 with 2 zeros plus an 80 minus a 45. Now, of course, that'll just here, this will just give us a 35, right? So we'll go ahead and compute that. So we get 2,435. Now, again, why do we bother to use the famous formulas? Why do we care? Well, because when you get to Riemann sums in Calculus 1, you will have to do these types of manipulations. And then you're going to let n pass to infinity. But of course, when you look at this one, you're saying that this has no hope. Okay, because this if n passed to infinity, this would just be infinity. Okay, so in calculus, when you do the Riemann sums, the limit of Riemann sums, you will actually have limits that exist. And this will be a way of introducing you to the area concept and the definite integral. So right now you look at this and say, you know, it seems a little bit untoward and maybe not so useful, but trust me, the study of series is tantamount to doing STEM. And of course, when you get to Cal 2 and then Cal 3, Cal 1, of course, and then your differential equations, and then beyond that, series will be extremely important. So again, the important part is the process. You know, it's kind of like if we think that everything that we do is just relegated to some technological device, then all we're doing is just pushing things around. Okay, you will always be in demand because you have a brain. Okay, and if you have the expertise of a STEM professional, then no one will ever push you out because you would have been replaced by a computer. That's just not going to happen. Um, it's amazing as we go through life, we always think about making, you know, things good in our society, and we think about having strong minds to produce good results. That's where you all come in. So what you have up here will always be in demand. Don't ever forget that. Now, so just remember, the other sequence that is of importance is the arithmetic. So I just want to remind you a little bit about that. It's a lot easier to work with, but just to remind you of the arithmetic, remember we had the first term. So this is arithmetic. And it doesn't matter as you work with these problems. For instance, if you're doing a word problem, like the one I did in lecture, you notice that it's arithmetic, and it usually is much simpler to think of it that way. But just to remind you, remember the A, just like with the geometric, was the first term. And then we had the common difference instead of the common ratio, the common difference. And so this gave us the sequence A plus D, A plus 2D, A plus n minus 1 times D, etc. And so just remember that we have, here's the general term, but we had a really nice formula for the partial sum, which you'll find useful. N over 2, 2A plus n minus 1 times D. So just like with the geometric, we have this nice partial sum, but clearly this would never converge. If n passed to infinity, this would just be infinite. So it kind of a lost cause. So again here, do not forget the arithmetic. Now, we don't spend a lot of time with it, but it is in the finite cases, it can be extremely useful. And I think you found that out when you were working on your homework. Now, there will be, of course, on the final exam, you'll have maybe one question with the binomial theorem, you know, or one question that has to do with the binomial coefficients, because I've talked about that forever. And of course, you'll probably have one question on induction, and it'll be set up so you just basically have to say something about the induction step. So what I wanted to do is now review a simple induction problem. And the divisibility type problems make good test questions because I can always phrase a problem that requires you to come up with the next step that will fit the format of our exam. Remember, there are 20 questions, so not a long exam at all. I decided to go on brevity this time, focus on the main concepts, and give you a test that has full coverage, but doesn't have tons of busy work. So now we have P of n that looks like this. We'll say 7n minus 2n, I like these multiples of 5, is a multiple of 5. Basically, and we'll say for all n, for all natural numbers n. Now, what does that mean? I gave you some notation. This means 5 divides 7 to the n minus 2 to the n. And the induction step here is important. And I want to review this. This is important. Often with induction, you have some variation on how you can affect the induction step. But here, the actual algebra that you use is very instructive because it's going to be something that you use quite often in Calculus 1. So for instance, again, we let S be the set that contains all the natural numbers for which this is true. So for instance, number 1 of our proof, we would let n equal 1. And so we just do the substitution. S to the 1 minus 2 to the 1. Well, that's 7 minus 2, which is clearly 5. And 5 divides 5. So we would say this implies that 1 is in S, or, well, 1 is an element of 1. 1 is in S, or this basically says P of 1 is true. So when we say 1 is in S, we also write P of 1 is true. So I have either of these ways to express this. And then for the second part, we suppose for some n in the natural number, sometimes we don't even say this part, we just say that n is in S. That is, we assume P of n is true for some n. This is where we have to get the domino effect. We want to get the induction step here. That is, we want to assume this and show that that forces this to be true for n plus 1. Again, that's the arbitrariness of the induction principle, okay? And that's the value of it, okay? We did lots of examples with this, and I think you'll find that induction is actually quite useful, okay? It lends some authority to your calculations. You know, people, your audience may say, well, why is that true? I mean, it seems true. And you say induction principle. So if we look at this, this basically just says, how can we think about this? This is a multiple of 5. And so you have this assumption, and then what you want to redo or rewrite is this replacing n with n plus 1 and showing that that difference is actually a multiple of 5. And what's the key? Well, you have to add and subtract. So when we write this, we just say that 7 to the n minus 2 to the n is just a multiple of 5. And so we could say 5 times phi, where phi is a natural number. Now, of course, if we're doing the entire process, we need this, but you can just say, we know this is a multiple of 5. So what would be the way to show that this is actually true if we bump up to the next power, n plus 1? Then we would say that 7 to the n plus 1 minus 2 to the n plus 1. And here's the key. Here's the main induction step right here. It's like, okay, so how are we going to be able to rewrite this so that we can use this? Well, I showed you that trick, the algebraic trick. We said 7n plus 1 minus 7 times 2 to the n plus 7 times 2 to the n minus 2 to the n plus 1. Now notice here, this is the key. This is basically the induction step. This is easy to test you on this. Because if you understand induction, you would know that this is the correct induction step. If not, and you didn't pay attention to anything I said, then you'd just be guessing, and that's unfortunate. But the idea is when you look here, we see, just like working with the series, these are equivalent because all I've done is add and subtract the same term. I've added 0 essentially. But what we see is that the 7 factors here, and we expose this, which is a multiple of 5. And if you factor the 2 to the n, then you just have 5 times 2 to the n, which is clearly a multiple of 5. So this is the induction step algebra. Induction step algebra. So this is the key. Often brute force will get you through the induction step. You factor, you add, common denominator, boom, then you see, oh, look, there's the n plus 1. You know, we get this sum is this, we're done, kind of thing. You know, that is good. But this kind of technique is kind of like the conjugate method, multiplying by 1, right? You know, we would say, like, for instance, if we have a cosine plus a sine, or we have a 1 minus a sine, we multiply by 1 plus sine, divide by 1 plus sine, so we can use the Pythagorean identity. This is the companion technique, where as opposed to multiplying by 1, we add and subtract the same term. And what that does is expose algebra that is not apparent when we look at that. Now, of course, you can start substituting values for n and say, oh yeah, that's a multiple of 5, but you can't do that infinitely many times. Your algebra has to expose the fact that this will always be a multiple of 5 if we have this setup. If we assume that this is a multiple of 5, then this will always be a multiple of 5. And then that's the induction step. So this is the critical part here, okay? And I wanted to make sure that you see that, because this makes great test questions for exams, so that I can say, okay, what's the induction step? What's the next step? And this allows me to test you, because if you don't understand induction, it makes no sense. But if you do understand induction, then this is precisely what you need to do. And now, just to finish it off, if I were doing like a face-to-face class where you were actually writing with your pencil and your paper, remember back in the olden days, this summer I'm going to try to do some face-to-face. We'll see if we have enough students to sign up. So here we can factor, in this case, the 7 out of both of these. So we have 7 to the n minus 2 to the n. And here we can just factor the 2 to the n using the laws of exponents. And this just leaves 7 minus 2. So this is critical. After this, it's just a matter of doing simple algebra. So often with the induction step, and this is where the variation occurs, you might be trying to do something by induction, and it's like, I have no idea how I'm going to do this. So you work with it. You work with it and test certain ideas. And so now, of course, this is what 7 times 5 by the induction hypothesis, plus, and of course, this is a 5, so this is 5 times 2 to the n. Well, both of these are multiples of 5, so this is clearly a multiple of 5. So if you wanted to, you could just say 5 times 7 pi plus 2 to the n. So this would imply that n plus 1 is in S, or P of n plus 1 is true. So the nice thing about your text is that it does make an effort to introduce the notation of P of n. I just add the S. It's not necessary, but it just makes the work a little bit more efficient, but you're always doing this. So in order to move this problem forward, as I've said before, the critical induction step algebra is here. So this would be what you would have to execute in order to complete the induction step. This is just icing on the cake. That doesn't require any knowledge. That's just basic factoring, which is an Algebra 1 student could do. But this is the critical step, okay? So now if we have n equal 1, P of 1 true, 1 is in S, we have what we assume true for n, that is n is in S, P of n is true, and we show that that forces P of n plus 1 is true, or n plus 1 is in S. So this would be all we would need. So by induction, we'll just say now S is all of n, or P of n is true for n in the natural numbers. So now you can see why this notation is nice and efficient. If we just assume it holds all the natural numbers for which P of n is true, it's saying exactly this. So the induction principle is a useful tool. However, it doesn't work for non-natural numbers. We can have real numbers in the mix, right? We can have real numbers in the mix, but there has to be the undercurrent of the natural numbers. That is, there's a first natural number for which it's true. Maybe it's 1, maybe it's 3, maybe it's 2, or whatever. And then after that, we get it valid for all the natural numbers, even though there might be some, like de Moivre's theorem, there might be a cosine and a sine and an imaginary unit, how we could raise the cosine plus I sine theta to the n and get a very simple result. So the key here is that this doesn't have universal application. And so you may look at it and say, okay, well, fine. But when you think about the fact that the inductive formulas, the famous inductive formulas that we used in the previous example are so important to calculus, induction does play a role. And so some of you may go on to do more discrete math. You may do combinatorics depending on if you're computer science majors. And so in some of you may minor in math. So you're going to take some abstract algebra and number theory and things like that. And of course, you'll see induction. Number theory and induction go hand in hand, because what's number theory? You're basically studying the natural numbers. Okay. Now, what I'm trying to do is focus on it. When I review for calculus 2, they get so tired of polar coordinates and the calculus of polar coordinates. We spend more time on the old stuff, but the newer stuff that we do in pre-cal tends to be pretty tricky. So what I want to do is an example with the binomial theorem. Now remember, the binomial theorem has lots of nice uses. It's great in the binomial distribution. Remember, we talked about throwing the darts. You know, that's a binomial experiment. You either hit the bullseye or you don't, and how the binomial theorem actually allowed us to compute probabilities. We can expand binomials. We can pick out particular terms of the binomial that we want. And then because of the connection to Pascal's triangle, we get a lot of nice theorems about binomial coefficients. And we figured out that if we can add the rows, the elements in the row of the Pascal's triangle, and we know what that is. I mean, I'll say more about that. So there are lots of uses of the binomial theorem, again, that you'll see. So here's a nice example. For instance, let's just look at the following. Here's an example. We have, this is just a simple expand. Expand, in this case, let me write it this way. This is going to be where we look for a particular term. So in this case, determine the term which contains, of course, you can do an expansion, but which contains x to the fourth in this case. So sometimes it might be written as the number of the term, or sometimes it'll say which term has this object in it. And here's the actual expansion. We have 3x plus 4 to the 6th power. Okay, when we look at this, we're thinking, okay, here's a binomial, 3x plus 4, a is 3x, b is 4, and we have n equals 6. So the binomial theorem says that we'll have k equals 0 to 6. 6 choose k. Again, we get Pascal's triangle. And then we have 3x to the 6 minus k. And then we have 4 to the k. Okay, so now the idea here is it's a matter of just looking at the formula. Again, you don't have to guess. If they wanted the particular term, we know if we've got n equals 6, then that means we're going to have 7 terms. We're going to have the 0 term, the 1 term, the 3 term, up to the 6 term. So we talked about that at the last lecture. Now, if we're interested in the term that contains x to the fourth, we just simply have to look here and notice that x will be raised to the 4th power when k is equal to 2. So we observe k equal 2 as the index. K equal 2 corresponds to term containing x to the 4th. So this is actually a good example. If you're asked to expand, fine, expand, get all the terms. But when you do a problem like this, you don't have to do all the expansion. That would be a waste of time. I mean, you know, you do all the terms, and the one term you need, you do incorrectly. And so that's unfortunate. We don't want that. So if we look at it this way and we analyze the theorem and what it tells us, we just basically want this power to be 4. And that means 6 minus k is equal to 4. So k must be 2. So now, so this implies we have what? 6, in this case, choose 2. And then we're going to have 3x to the 4th and 4 to the 2. So there's the term right there. Now, of course, when you're looking for answers, you might say, oh, well, maybe the answer is listed this way. I'm done. But if it's not listed this way, then you need to look at it and say, well, let's reduce this to numbers. Now, here's the thing. X is the only variable. So there's going to be an x to the 4th, and then there's going to be a coefficient. So what I'm going to say is determine, so say you looked at the answer choices, determine the coefficient as an integer. So the key here is this. You're obviously going to see that there are a list of answers, and you're thinking, okay, well, let me work it out. And you get to this point and say, well, okay, I know how to compute binomial coefficients, and I know the laws of exponents. So this would be the next step. So this gives us what? 6 choose 2. That'll be 6 times a 5 divided by 2 factorial. That's for n choose k. We'll say n perm k divided by k factorial. And that just gives us n times n minus 1, etc., down to n, in this case, minus k plus a 1 divided by k factorial. So when the number here, the k is small, this is an easy computation. And then, of course, we like to use the fact that n choose k equals n choose n minus k. Of course, when k's kind of halfway in between, this is not very useful. But if k is on the extreme, like this is large, closer to n, then this will be a simpler calculation here. So of course, what we want to do is that make use of this when it's going to help out our calculations. And here we're in good shape. We can't simplify that any. And so now we have 3 to the 4th, x to the 4th, times the 4 squared. So now, of course, the 2 absorbs into the 6, so that gives us a 3 times a 5. And of course, this will give us an 81. That's our friend from the previous problem. And then, of course, we have, go ahead and move this over, we get a 16, and then an x to the 4th. So this is a little bit closer to what we need. So now what we can do is break this down. So this will be a 15 times a 16. So we have, in this case, a 10 plus a 6. And then we have an 81, so we can do that as an 80 plus a 1, x to the 4th. So now if we look at this, this is actually quite doable. So we have a 150. And then we can hit this with a 6. So again, that's our friend. That's going to be the 80. So we have 6 times 5 is 30. And then the 3, well, that's actually the 90 in that particular case. And so now when we look at this, we can say, okay, well, this multiplies the 80 plus the 1, x to the 4th. So now we can go ahead and multiply this out. So we have what? 8 times a 5, that would be a 40 with a 4. So that's a 1, 2, and then add 2 zeros. And we'll just go ahead and do the FOIL method here. That's kind of interesting. I set it up this way, so I'll just do FOIL. So then I've got a 150 times 1. And then we have the 90 times the 80, so that'll be a 72 with 2 zeros, and then the 90. Since I wrote it as a FOIL, I'll just write it that way. So we can add these up. So now, of course, we've got, in this case, let's go ahead and put these two together. So that'll be a 0, and then that'll give us a 14, and then a 1, so that'll give us a 240. And we can add these two. So we've got 2 zeros, and then we have the 2, and then we have the 7, that's a 9, and then a 1. So now we can add this up. So this will give us a 0, and then here we've got a 4, and then a 2 and a 2, which is a 4, and then a 19. So the key here is that we don't have to go through all of the terms in the expansion. Clearly, if the problem said, okay, stop here, and that would certainly be a good way to do it if you think about it. You know, this would be that, oh, well, you know the theorem and you know how it's stated, and this is certainly equivalent. But when we look at something like this, maybe we have a colleague that says, well, can you write this as a number? You know, it just depends. Or maybe you have a client, you're working with them. It's kind of like a lot of you may end up doing finance or something, or have some work with business eventually. And so we have to work our arithmetic and our mathematics so it's palatable to someone who may not live in the STEM world. So again, just remember, you have the power of the binomial theorem. You have the power to manipulate here if necessary. If you start with this, you can go directly to the theorem. And if you're looking for a particular term, so maybe they just said, what's the third term? Well, the first term is k equals 0, k equal 1, k equal 2. Well, this is the third term because we start with 0. So that would be another way of phrasing it. But this kind of pinpoints it. It's like exactly, okay, which term is going to contain this? Now, there was something that I mentioned about Pascal's triangle. And this is an important construct. So when we set up Pascal's triangle, the the Pascal's triangle is completely related to the binomial expansion. And so we found that when we started writing the triangle, we can do this. So on the outside, on the legs of the triangle, so to speak, they're all ones by definition. So we have 2, 0, 2, 1, 2, 2, and then 3, 0, 3, 1, 3, 2, 3, 3, 4, 0, etc. Let me just write another row. So when you look at this goes on ad infinitum, but you're seeing that this is intimately related to the binomial expansion. Let me click there we go. Looks a little better. And so I talked about this last class. And so we can see that the binomial theorem allows us to add the elements in the row of the triangle. And we found it to be very simple. That is, for instance, here's an example. Say you had this. You have, say, k equals 0. We'll just do the last one, to 4. 4, choose k. Now, if you were asked to do this sum, you'd be like, oh, okay, well, I can just I can just write all these out and add them up, you know. But it's much simpler than that. We had that nice rule that basically this sum is just replacing A and B in the binomial theorem with 1, each with 1, and 1 plus 1 is 2. So we know if we write this out, this is 4, choose 0, plus 4, choose 1, plus 4, choose 2, plus 4, choose 3, plus 4, choose 4. But that's just 2 to the 4th, which is 16. So the power behind this particular result here is that it doesn't matter what that number is. You can always compute it. It's just going to be a power of 2. And of course, this is the setup. This is basically the sum of the row 4 of the, well, actually for n equal to 4. I mean, it's actually the 5th row because we start with 0, but this would be the n equal 4 row. And we have our 0 row, 1, 2, 3, 4, etc. So when we did this result here, that's the power of doing the mathematics. This is the power of using the binomial theorem. And then, of course, when we did the alternating sum, we got 0. So the key here is that why did this even work? And we proved this. Remember that n choose k minus, well, let me shift it over a little bit. N choose k minus 1 plus n choose k. So that'd be like saying 3 choose 1 plus 3 choose 2 is going to be 4 choose 2. So this is going to be n plus 1 choose k. This is Pascal's identity, and we proved that. So this is Pascal's identity. And the thing that's good about this is that this allows us to build this triangle. And then, of course, the binomial theorem allows us to get this result. So the interesting thing is when we do this and when we fill in all these numbers, we can generate the Pascal's triangle very simply. And of course, you computer gurus, as you do, the coding is fun because it's just mathematics with a computer language, and you could generate a triangle as many rows as you wanted. And of course, these numbers get big really fast. I mean, the numbers get larger and larger and larger, and computers are really good at churning out numbers. And especially since this is integer arithmetic, you don't have all the problems with round off as long as there's sufficient memory. So just remember that we have new computational abilities because of the binomial theorem. And that's really the power of math. Usually trying to find the sum of a series can be very difficult, especially if we want an exact formula, okay? That is something that is a luxury, okay? And so normally what we do, we're more than happy to get a reasonable estimate of the sum within a certain number of decimal places to do our engineering project or do our math problem or whatever. It just know that these beautiful formulas that we get, especially for the partial sum of the geometric series and the infinite sum, those are the exception. And so you will find that out as you do more and more. But when you learn a new sum, when you learn a new result, you remember it because you know there aren't so many of them that it's going to get in the way. So again, this is a nice result. Binomial theorem is useful. You've been using it from day one. When you get to the Newton binomial theorem in Calculus 2, you're going to have more understanding of how your calculator works. And I'm a big fan of that. Now, I want to say, again, I'm trying to focus on things that either are new and tricky or things that I know you'll have some issues with. Now, remember, you got word problems and things, and so everybody's good at that. Just remember to write your own solution. If there's just going to pick and choose, I might put a time, rate, distance. I might do a mixture. There'll just be one. So as you go back through the test, just work through the basic construct. But you all got that beaten into your head in college algebra. But again, please do your own work. Write up your own solution. Let me be able to look at it and see that you've logically deduced. That is very important for the final exam. I certainly don't need to repeat myself. Now, one thing that I thought was kind of interesting, remember, if you have the inverse trig functions, you can use the sum and difference formulas like we had on the last test. A lot of you did a much more elaborate solution, which took you forever. Which I didn't teach you. I just used the triangles, and it was a one-liner. But here's a simple example, which basically attests to the composition computations that include the inverse trig function as the inner function. So remember, in this particular case, we flip it around. Now, of course, before when I would do this, we would have the inverse trig functions on the interior, and then we'd make our triangle assignments and then use the sum or the difference formula with tangent or sine or cosine. That's a very, very nice strategy. But here we would just say compute the exact value. Now, of course, these are fun problems and you did these with your homework, and this requires that you respect the range and domain of the inverse trig function. So we remember when we did inverse trig, that is, we have inverse cosine of x lives between 0 and pi. That is our definition, and that's a standard definition. And then, of course, we know that the domain is between -1 and 1. So this is the range, this is the domain. And then, of course, we had the inverse rules, which you all know. I know I sound like a broken record. So we'll have what? Cosine of inverse cosine. Now, of course, this has to be in the range of the cosine, which is what? In -1 to 1. So we'll say x, if and only if x lives here. So again, this x, if this is true, must live in the range of the cosine. 2, if we flip it around, inverse cosine of cosine of x. Again, this will be the identity if and only if x lives in the range of the inverse cosine. So these are not always your friend. When it comes to doing these types of problems, you're like, well, my goodness, we have to obey this. Of course, we have to respect the mathematics. And if we don't, we don't get correct answers. And then our, computations start to fizzle out. The important thing is that when you think about most of the work that you learn in mathematics and the work that you learn in science, it's that everything is based on some logical convention. And the only reason we have the conventions is that we're all on the same page, so to speak, that we use a similar notation. In biology, in chemistry, and physics, you use a standard notation. In engineering, you will use a standard notation. And those of you that go on into maybe pharmacy or medicine or whatever, you will use a standard notation. So when we go over here and we do this computation, we're like, okay, well, 4 pi over 3 does not live in there. We're thinking, that's not going to work. So the first thing we want to do is make an adjustment here because we know that this cosine function is defined for all real numbers. So first, we can look at this and say, this is in the third quadrant. That is, if you want to look at this, that's pi plus pi over 3, which sticks us into the third quadrant. And so you can say here, if we wanted to say 4 pi over 3, if we don't give it a name and we just do the bar, so to speak, this will be 4 pi over 3 minus pi, which is pi over 3. This is the reference number or the reference angle. And of course, this is in the first quadrant, but we know that in the third quadrant, the cosine is negative, right? So this will equal inverse cosine of the negative of cosine of pi over 3. Okay, so that's really important. And now we have to use the fact that we understand how the inverse cosine works with the negative argument. And that's another identity I've talked about. This will be pi minus inverse cosine of pi over 3. So this problem is necessarily more complicated because, again, it's not user-friendly. But I mean, you can always just punch this in a calculator and get an example and you'll get 0 points for that. Okay. And then of course you can write down some nonsense and get 0 points for that. So the important thing here is not your ability to punch buttons on a calculator. I don't do that. And you shouldn't be doing that much. The idea is that now we have something that makes sense. That is, we have now adjusted this using the reference angle, applying the arithmetic of the unit circle, and then we use the fact that if we have a negative angle here, the inverse cosine is not odd, it's not even, it's just in trouble. But we do know that we can use this particular identity. And so now when we look at this adheres to this rule here. That is, pi over 3 does live between 0 and pi. And so now we get pi minus pi over 3, which is 2 pi over 3. So when it comes to doing these types of problems, and I'll say this, there was an example, or was it on the last test? Yeah, on the last test, like I said before, there was the example where all of the inverse trig functions were on the inside and you use the triangles or whatever. That is actually a more user-friendly problem than this will ever be. Again, what we have to do is be able to use these rules, especially this one, because this is the difficult one, where it makes sense. And so when you apply this rule, you have to think about the arithmetic of the unit circle. And then we go back to convention. again, remember, this inverse cosine function is pretty strange. If you take this and think about the picture, remember when we wrote all of these functions down and thought, oh my gosh, this is really different. We got what? -1, 1, and then we have the pi over 2 and the pi. So we've got this strange function here. So this picture, again, we just get by reflecting in the line y equal x, and my picture is not the best, but it'll work. So why you're thinking, do we do this? When you get to Cal 2, you're going to study the calculus of these functions. You may get a little bit of this at the end of Cal 1, but you're going to study the calculus of these functions. And the thing that's interesting is that even though we've gotten this by default using the cosine function, all the calculus will verify that this graph is indeed decent. Okay, so we have to kind of stand back and say, well, this is kind of the best we can do in pre-cal. We don't have the luxury of calculus, but you do have the luxury of the definition and how we define the inverse equations. And these techniques will be very important when you get to calculus. You might be doing an integral and you've got to draw a little triangle. For instance, say you're working a problem and you draw a little triangle here that you have in your problem. And when you're doing your computations and you change your limits, you have inverse cosine. In this case, let's just say here of 2/3. So you get that as a limit, okay? And so, oh, pre-cal. So you go over here and you think of this as a theta. So when you did your calculation, this is what you ended up with. And you're like, ah, well, it's exact. I'll leave it that way. So you go over to your triangle and you say adjacent over hypotenuse. So you have 2 and 3. And then, of course, this is a 9 minus a 4. So this is a square root of 5. Now, say in your answer, you end up with this term. So we'll just say in the response, it includes the following term. It includes tangent of inverse cosine of 2/3. And you're thinking, well, good. I know what that is. This is just tangent of theta. So you're doing a calculus 2 problem, and you have this in your response to the definite integral. Well, you go over here and you just say opposite over what? Adjacent. And this will be square root 5 over 2. And you know exactly how to interpret it. So that's exactly why we do this now. Because when you get to Cal 1 and especially Cal 2, you will see all of this stuff again. And it would not make any sense for you not to have seen this before. That's why we call this pre-calculus. And so the understanding of the arithmetic of the unit circle undergirds the understanding of the inverse trig functions. And without it, again, you know, when I teach calculus 2, and it's one of my favorite, well, I like all the math classes I teach, but it's one of my favorites because it's basically a testament to the pre-calculus you learned, the trigonometry. And I've had many students say, oh, I'm no good at trig, Professor Ron, I don't like trig. I said, no, you're fine at the trig. They don't like the fact that they have to be so vigilant about the arithmetic. And it is kind of a pain. It is, but it is something that we are stuck with. We are stuck with trigonometry, and until someone comes up with a better way to define angles and consider the relationships between circles and triangles, we're stuck with it. And it is a beautiful, beautiful subject in mathematics. So again, just remember that all of this will come back to you. And you're going to love it when you've got these, when these make sense, you know, oh, that's X, you know, but you're going to have to, in the back of your mind, make sure, okay, are these restrictions correct for this problem? So all of this type of analysis here will be what you will do in Calculus 1 and Calculus 2, and all these triangles and things that you use to evaluate will come back. So I want you to know that what I demand of you in this class is so that you can have success in calculus. It has absolutely nothing to do with the fact, oh, Professor Ron is difficult. No, no, this is what you have to be able to do to execute calculus. And it is really, really unfortunate that you get to calculus and you do not have an understanding of this. And that is the reason when students always say, well, he expects for you to know what you've learned before. Well, precisely, because prerequisites are set up for a reason. The prerequisite to the class is standard knowledge to do the next class. And if you don't have the knowledge of the prerequisite class, you won't be able to execute the next class with the success that you want. So, and I know it varies. Every class you might think, oh, the prerequisite, I've got that, you know, no problem. But it might be in a subject area that you spend a lot of time with. You know, people always say, but everybody studies math. You study math all through school, but that doesn't make any difference. You know, the key is that you study math in a way that you retain it. Okay, there's a big difference. Why do we spend so much time on math and languages? Because they're difficult. They are difficult. They are the bedrock of everything that you want to do. So just remember, the next time someone's putting down the math class, correct them. Okay, so when I was writing the test, and I stayed up late this last night to finish it up, again, the basic constructs that I kept going over and over were just very simple ideas. And one that I thought was interesting would just be the logs and the exponents. And I thought to myself, what would be a good way to test my students on that? And so I'm thinking just the basics. What's a logarithm? It's the power of the base. So here's an example. Here's an example that will be useful. I will say this, the applications that we did, the interest, the growth and decay, Newton's law of cooling, things like that, there will be a selection of one of those. Okay, I can't test you on all of it. Okay, but those are important constructs because the understanding of doing that particular problem requires that you know what a logarithm is. And that is our bread and butter. So let's look at a simple example just to remind ourselves of what a logarithm is. So we'll just say solve in R, or just solve. So we did a lot of very extravagant equations in this class. And of course, the equations on the final will not be as extravagant, you know, because of course, this is a more widespread test. But if you can do those and you can change the base, that's fine. When you get to calculus, you'll change the base and you'll realize why we even bothered to talk about it. Now, this is just basically the definition of logarithm. If we solve this equation, we've got a base 4 logarithm of x squared minus 3x equals 1. Well, what's a logarithm? It's the power of the base. So we know that the power of 4 that equals x squared minus 3x is 1. So we just write down the equivalent equation. So x squared minus 3x equals 4 to the 1, which is 4. So now we've got x squared minus 3x minus 4 equals 0. Now just remember, when you're solving equations, especially with polynomials, you know, I may give you a 0 and then you have to divide to figure out the other zeros using your division techniques. That is a good way to test you on the final, and it covers all the bases. So when we look at this, we can think of Professor Ron's AC lemma, but you can just see that -4 and 1 will work because we have -4 is just -4 times 1, and that gives us the -3 that we need. So don't always count on factoring being this easy. So we have x minus 4 times x plus 1 equals 0. So just like we do with trig equations, we just don't have to work as hard. And we'll go back and pick up a trig equation. So we have what? X equals 4 or x equals -1. That is based upon this quadratic equation. These are the zeros. Now, when you look at this and you think, okay, well, all right, and yeah, let me write the 1 here. When you look at this and you look at this equation in its own world, it's fine. So then we go back up here and we just make sure that everything looks good. Of course, the 4 here will retain a positive here. We've got the 4 squared minus the 3 times 4. That's positive. So this gets a check. And then the -1, again, when we look here, the negatives absorb and we still get the positive input. So I like this problem because, again, it doesn't matter that the input is negative. What matters is that the argument is positive. And in both cases, this happens to be the case. So this implies that our solution set would be 4, -1. Or sometimes, you just write the solution set or the solutions separated by a comma. Now, what I found with the final exam is that there's usually a single trig equation, or there's a graph or something of that nature, and the trig equations turn out to be pretty good. And you all are fairly adept at doing that. And the type of equation that would be interesting would be something like this. Say we had something like 2 sine squared x equals sine x. Now, some of the more popular identities that you're going to continue to use in calculus that will turn up often. For instance, we have the very famous cosine of the double angle. This is the cosine squared x minus sine squared x. And then, of course, we can replace the cosine with 1 minus sine squared to get this. This gives rise to the power reducing identities. And then, of course, replace sine squared with 1 minus cosine squared. So that gives us this. Now, you won't forget all of this, but when you get to calculus, all of this will come rushing back, and you'll be glad that you've seen it before. But just remember that don't spend an inordinate amount of time on topics that you understand. Remember, there are 20 questions, and I'll just do the highlights on this final exam. So when we look at this, we think of just how we solve equations in college algebra, and we say, well, this is just quadratic in sign. So if and only if we have 2 sine squared x minus sine x equals 0. And then, of course, we can factor this. We can just factor 2 sine out of both of them. So this leaves us with a sine x, and this will leave us with a minus 1/2. Again, when we multiply, we get the negative sine x, and here we get the 2 sine x squared. So this is equivalent. So again, the 2's not really important, but certainly that minus 1/2 is. So equivalently, we have sine x. And in this case, let me check the actual problem. In this case, we want to solve in 0 to 2 pi. And if it says solve for all, I'll give you a letter. For the integers, it'll be a k or an n, so that'll be clearly stated in the problem. So we have sine x equals 0, or sine x equals 1/2. I had a student that had an interesting way of doing Professor Ron's lemma, when you've got the different solving the sine and the cosine, and I thought it was pretty interesting. Everybody always has their take to remember these. And usually I've stuck with the nice values, but if you don't have nice unit circle values, the Professor Ron's lemma still gives you the exact answer, as we saw when we went through the lecture problems on that. So you always have that luxury of being able to write an exact answer. Now, of course, this is our friend because we know that the sin x function is 0 along the x-axis. So if we were solving this completely, we would say that x is just equal to, in this case, n pi or k pi. I'll use n this time. So n pi, where n is an integer. You can use k or n. So this is a standard construction that we have via the unit circle. So this would imply, at least if we're going to stick to this unit, we'll have, or this interval, we'll have 0 and pi. Now, of course, here we have x, and we like the inverse sine function. It's nice and user-friendly. So when we would do this, we think, okay, if we wanted all solutions, we could just say 2 pi or 2n pi, 2 pi times n. And of course, the inverse sine of 1/2, that'll give us pi over 6. And now by Professor Ron's lemma, we also have, in this case, x equals, in this case, we're in the upper arc. This is in the first quadrant. We have pi minus pi over 6 to get the second quadrant solution, which is 5 pi over 6. So let me just go ahead and put in the notation of the all, just to make it, I'll put this in parentheses and write it this way. So 5 pi over 6 plus 2 pi n. Now, of course, we want to restrict, and we've got more than we need. So, of course, when we start adding 2 pi, we go right out of this. So we only get n equals 0. So that gives us pi over 6. And here, of course, only n equals 0, since these aren't multiple argument trig functions, 5 pi over 6. So now this implies if we just put these together. Now, of course, remember, if we have a setup where we've got quadratic and we've got a way to consolidate, remember, if things differ by pi, you can consolidate them to give a more efficient answer. So don't forget that. I've spent time on that too. So there are ways to write an answer that are very nice. But of course here, when we're restricting to this, these are all mutually incongruent modulo pi and 2 pi. So we can just say 0, pi over 6, 5 pi over 6, and pi. And I think that the understanding of the basic trig equations has actually been fairly good that I've seen. Again, to get credit, you can't just write this down and say, oh, well, here are the answers. I just looked at the responses and these work. That is never going to be a solution. You have to work it out, okay? The beauty is that you have a list of responses from which to choose once you've completed the problem. Again, I'll never understand that. Again, just remember the format is to assist you making your final selections. You know, you just see, okay, here are the selections. Okay, let me get to work. It's like, oh, well, these are going to be written in terms of pi, and they're going to use k or they're going to use n. I'll keep that in mind as I do my work. But you do not work backwards from the problem. Only thing is you're looking at some form and say, okay, these are exact calculations. Let me do this the way Professor Ron did this problem so I get an exact answer. It says, round to 2 decimals. Okay, great. I'll go ahead and work it out. And then I can use my Google calculator at the end if I need to get an approximation. Okay, so what's important is technique, the technique of the logical deductive reasoning. That, my friends, that, ladies and gentlemen, is what I'm looking for. So it would be much easier for me just to ignore looking at any of that, but it's not a math class then. Okay, so just make sure, just envision the fact that you're sitting in a classroom, Professor Ron's at the front of the classroom, and you're working out your problems, and you're going to turn in your paper. It's the same thing. And I give you extra time to do it. I give you 30 minutes. Okay. So make sure you scan your work, and the majority of you have done an excellent job at that, and I appreciate it. Scan your work, make your one file, and upload it. And that way I have the luxury of being able to download your file. If I want to put it in a PDF form, I can download it. Sometimes you all put in files and you've got things oriented all different ways. Some pages are upside down, and it's a mess. So I download it and reorient the pages so I can read it. But if you don't give me a file, then I can't do any of that. And so I'm not asking you to do any more than just turn in your paper once you finish your test. Somehow I think that people feel offended that they have to turn in your work. If you took a test in a face-to-face setting, would you walk out the door and throw your test in the trash can? I mean, I just don't get it. So just remember that I'm not asking you to do any more than you would normally do in a class. But even if I were, it wouldn't matter. It wouldn't matter, because the rules of the class must be executed. Simple as that. Okay, so what I wanted to do, there's another example here that I thought would be interesting. Where is it? It's one that has the, oh yeah, the algebraic expression. Let me grab that. Let me get the exact expression. Yeah, here we go. Because it's been a while since we've done this. The trig was the hardest thing we did. And the algebra you already knew how to do, and the logarithms probably the second most difficult thing, but you were still pretty good at it. So in this case, here's an example. Here I want you to write, and you got a lot of practice with this, an algebraic expression for sine of the inverse tangent of x. Again, this is going to be something you're going to do a lot of. Probably there'll be cases where you'll have the more elaborate ones with the addition and difference formulas, but then this will be something again that you'll see in calculus. So again, we can make in this particular case, a substitution. Now notice, we know that this lives between -1 and 1 because this is the sign of this as far as an algebraic construct, but we can think in this case, theta is the inverse tangent of x, which of course will live between -pi/2 and pi/2. Now, what's interesting about that is that this aligns with the sine function, at least algebraically. We know that in the fourth quadrant, the sine function is less than 0. In the first quadrant, the sine function is positive. And so we just want to make sure that whatever we have here adheres to the algebra of the sine function and the inverse tangent function. So now equivalently, we have tangent theta in this case is equal to x, and we can write x over 1. Now this is where when we look at it this way, we're thinking of a reference triangle. Again, a reference triangle exists in the first quadrant where everything makes sense. And so when we draw a triangle here, we are focusing on the fact that it lives in the first quadrant where it makes sense. But that doesn't preclude the notion that the value of x can possibly be less than 0. But we're affixing this in the first quadrant so we can get the relationship between the variables. So now, which is what we've done from day one. So here we have a theta, and we have what? Opposite over adjacent. So we get this. And now, of course, we just sum the squares and square root it. So now we have our triangle, our reference triangle in the first quadrant. So this implies, or equivalently, sine of inverse tangent of x is just what? Sine of theta. So sine of theta will be opposite over hypotenuse. Now, of course, this has the appropriate algebra for us. So of course, when x is less than 0, so is the sine. So this has the correct algebra to work here. Now again, when, like I was saying before, when we actually got an exact value, you might be doing what we call an indefinite integral. That is where you actually, your answer is actually a function. And so you may be interested in relieving your answer of these kinds of objects. So you don't want to write your answer this way because the original problem was just algebraic, that it had x's and square roots and squares and Pythagorean this and all of that. So what you would do, just like we did in the previous problem, is that you've got this expression in your answer, and then you say, okay, let's go to this construction, and then have a way of rewriting this algebraically. And so this is what ends up in your answer. And this has the same form as the original problem. So I kid you not, this technique will come back and you'll do it with confidence. You'll do it knowing, wow, I actually understand this. So remember, logarithms power the base. Trigonometric functions, unit circle. Even if you're working with triangles, we just see the luxury of the right triangle and using ratios. Okay. Now, since there's a really hard to fit in all these types of problems, I'll go ahead and let you know that there will not be a problem with the law of cosines and the law of sines. I've beaten you to death with that. And that's not a benchmark type of problem that we do in terms of what you'll have to do in calculus. So I'm giving you relief of that problem. You can certainly study it, but you will not be required to do that on the final exam, just to give you a little leg up on that. I will say that of the 20 questions, the major types of problems are focused upon the conceptual understanding of the conic sections, where you have to know the relationship between the foci and the vertices, like for a parabola, for a hyperbola, c squared equals a squared plus b squared. We have those conventional equations. You have the new material with the binomial and the arithmetic and geometric, all very standard, I would say, foundational problems that focus on the critical reasoning. None of the problems that I've looked at on the test I consider to be overly difficult. So I think that when you prepare for the final exam, focus on the examples where you need the most work, okay? Where you need work. Don't look at things that you can do in your sleep. And there won't be a lot of instances where if I ask you to factor a polynomial, it'll be because I'll give you a 0, and then you'll have to work to find the other zeros through division. So I'll test you on the division algorithm. I'll test you on complex zeros or imaginary zeros, all of that in one swoop. So you get very focused problems that cover lots of techniques, but very straightforward problems. So I think you're going to be in good shape. Let me also remind you that I've given you an extra day for the homework, the last 2 sets of homework. I always say on the assignments, complete any remaining WebAssign homework, and that means whatever's been assigned this week, you've got till Thursday. And there are no more extensions, so don't ask for them. At this point, you should be good, okay? I was more than happy to honor those during the semester, and there were many of them. There were too many of them. Let me just make this comment. It's important, as I said before, to be current. You want to make sure that you put your best foot forward. And just remember, I'm a very reasonable person. but it's better to stick to the schedule and be upfront about your work and own what you do. Okay, that is going to make you a STEM professional of note. Okay, you want to always go to your boss and say, I'm ready to go. Okay, you don't want to tell your boss that you can't do it or you don't have time to do it or whatever. Then your boss is going to say, well, okay, well, then maybe you're not a good fit for our outfit, kind of thing. I don't want that for you. I want you to be current with your work. I want you to always bring your best to your class, bring your best to your job, bring your best to whatever you do. Ladies and gentlemen, that's called integrity. I'm not asking you to be perfect. Nobody's perfect. I'm asking you to bring your best. And if you've done that, and students often send me emails, I say, what can I do to improve? I said, just do your best and stay consistent with the work. The idea is that if you know that you have a difficult class, you should focus on it every day, even if you've got a million things to do. You know, when I've got a million things to do and I've got all these tasks to do, I still carve out the time to do them. And I may be half asleep when I'm doing it. I may be tired. I may need to just go to sleep, but I've got to knock it out. And just remember that not every week of your life will be crazy. Some weeks will be very intense, but you know what gives you that lift? What gives you the lift is that at the end of the week, you can sit back and say, I've done my best. And that just gives you a springboard into the next week. Why do I say this? Because it's the truth. And it's a matter of understanding how you navigate life. And life is difficult. And life as a STEM professional is even more difficult. But you have a wonderful, rewarding career ahead of you because you have chosen this curriculum. And I salute all of you for working hard and bringing your best to the table. So I will send out some invitations for the conference hours today. Most of you are so brilliant, you don't need my help anymore, but I'm always available. Send me your WebAssign messages for questions if you have them. And so I wish you well as you study. Thank you, and enjoy the nice weather. It's kind of hot, but I think compared to what we're going to have in the summer, it's pretty cool. So everybody have a great day, and thank you for your attendance.